An accelerometer measures how quickly the speed of a vehicle is changing in time. And if you know that, then by some simple mathematics you can work out what the position of the vehicle is. The idea of navigating using an accelerometer is actually a pretty old one, but it has the difficulty that you need an extremely precise and reliable accelerometer if you don't want to make an error. And the longer you go, the more the error compounds. So pretty soon you don't have a clue where you are. We need new types of navigation because at the moment the world relies very heavily on the global network of satellites to tell everybody where they are. And it's actually rather easy for that system to be emulated, and in fact it's been estimated that the UK alone stands to lose about £1 billion a day if the satellite navigation system were denied. We have just made the first quantum accelerometer for application to navigation. That's a device that measures acceleration using ultra-cold atoms.
So when the cloud of atoms are very cold, we have to use quantum mechanics to describe how they move. And this allows us to make what we call an atom interferometer. Then if the vehicle that the atoms are inside is accelerating, this changes the way that they move, and we can use precisely controlled pulses of light to read out how the atoms are actually accelerating.
This laser was purpose-built by M2 Lasers for operating an atom interferometer. So for an atom interferometer you need two things. The first thing is laser light, which cools the atoms down. It takes atoms that are hot and makes them cold, so their quantum behavior starts to emerge. The second thing is a laser beam that acts as an optical ruler to measure the position of the atoms as a function of time. If we do this, we can measure the atom's position and therefore acceleration, and therefore we can navigate with a system like this. So for an atom interferometer, you need optical pulses that are high power and also very precisely controllable in their frequency, amplitude and phase. And this laser does all those three things.
At the moment we measure acceleration along a single axis, but soon we want to extend the system to measure three orthogonal accelerations and also three rotations, so that we can build a completely independent navigation system.
I think it's tremendously exciting that this quantum technology is now moving out of the basic science lab, where it's already been exciting for a long time actually, but now it's being applied to problems in the real world, and not just navigation, but measuring gravity, mapping the gravitational forces to look for minerals, possibility of looking inside vehicles to see if there's something shouldn't be there. There are many real-world applications that are just beginning to emerge, and they all come from the fantastic sensitivity and reliability that you can only get from these quantum systems.